Hey guys, Dr. Brown here with Kubo Math coming to you from Tarlac City, Philippines. And tonight we've got Calculus 2, Numerical Integration. Whoa! Specifically, the trapezoid rule. Now later we'll look at Simpson's rule in another video, but tonight we're going to introduce you to numerical integration trapezoid rule. Why? Why are we doing this? Because, we've looked at problems where we do U sub, trig sub, integration by parts, partial fractions, you name it. We've been doing it, okay? Completing the square, that's 5. That's the 6th one. I can't remember it offhand, but we've been doing a lot of that. Now, I'll tell you a little story here. I spent 20 years working as a technician from age 10 up until age 30. By the time I was 30, I had 20 years of experience doing that. So at that time, here I am in electrical engineering college, and the teacher says, well, given this transfer function or this mathematical statement for machine A, do this, calculate this. And I said, excuse me, I've been working in the field for 20 years. I've never seen a math equation on any machine, any of them. He said, well, that's interesting. You should say that because in my class, I'm going to give you the machine and you give me the transfer function. You give me the math statement. That was a great class because after I graduated, get out into the engineering world, I spent years perfecting the ability to take data and do regression analysis, multivariate analysis. You have to be able to take data. So in this case, I have ordered pair data, X and Y's. How do you take that and get the area under that curve? We're used to saying, okay, I have, x cubed plus 2x minus 5. And I'm going to integrate that from 1 to 5 with respect to x. Well, how do you take that and get to that? That's what we're going to talk about tonight, which is an interesting concept, okay? How do you do that? Well, fortunately for us, there were some smart people out there that came up with numerical integration. What if we had that data and let's say we end up with a curve that looks like that? Okay, maybe, let's see, this will be f of x and this is x. And that data, we plotted it out and that's what it looks like. Now what? Your boss said, hey, Steve, I need to know what the area under the curve is. We want to look at that data from here to here. Maybe this is A and that is B. This is this year's worth of warranty data. Hopefully that's not what your warranty data looks like. You'd like to think that it's getting better over time, but yeah, it's not. You got a problem here. So we need to analyze that. Okay. If you think about an integral of f of x dx from some limits a to b. Remember, delta x is some width. Excuse me. F of x is just the height of the function at some point. And they're evaluating this from a to b. Well, if we were to set up and divide this thing, just like when we learned integration to start with, if we divided that into various segments, and just imagine each one's the same width, my artistic ability is limited, okay? Well, if we said delta x was b minus a divided by n, wow, that's this. That times f of x would give me then the area in that particular box. But I can do better than that. I can say, let me get the let's let this little section right here be f of x sub 0, and this one be f of x sub 1. Okay, well, I could say, all right, my area then is f of x sub 0 plus f of x sub 1 over 2. So I'll get some average of that, times delta x, which is b minus a over n. Okay, that's the area of that first block. What about the second block? You know, this point right here is f of x sub 2. So now I have f of x sub 1 plus f of x sub 2 divided by 2 times delta x. Okay, well, that gets the second one. Now I have this point right here's f of x sub 3. You can see how this is going. F of x, oh sorry, that's f of x sub 2 plus f of x sub 3 over 2 times b minus a over n. Well, this keeps going like that. Now I have f of x sub 3 plus f of x all the way up to n minus 1 over 2 times b minus a over n plus f of x sub n minus 1 plus f of x sub n over 2 times b minus a over n. Sorry for the writing, I'm stretched out here, about to end up without a cord. Well, what's in every one of these? Well, I could factor out the b minus a over n. Let me do that. So I've got b minus a over n. Well, if I do that and I take all of those out, I still have it's over 2 in every case. Let me factor the 2 out also. So what does that leave me? Let me just wipe that out up here. And I think you're going to see something interesting. Get rid of all of these here because we factored it out. All of these, all of that's factored to the front. All right. What do we have left? F of x sub 0 plus f of x sub 1 plus f of x sub 1. So I have 2 of those. Plus f of x sub 2 plus f of x sub 2. I have 2 of those. And that's going to happen all the way down to of the f of x sub n minus 1 plus f of x sub n. You'll notice when I got to the end, I didn't have another one of those. That, my friend, is the area under that curve calculated numerically. Let's challenge that. Okay? All right. Let me get us a workspace going here. All right, what if I have a function that says, let's say the integral, keep it simple, x squared dx. And we're going to look at that from 1 to 3. All right, so if we integrate that, x to the 2 plus 1 would be to the 3rd power divided by 3, or multiply by 1/3. And we're going to look at that from 1 to 3. Well, that's 1/3 times 3 cubed minus 1/3 times 1 cubed. So I have 3 cubed is 27. I have 27 over 3 minus 1/3, which is 26 over 3. All right. Let's assume for a moment n. I'm just going to break this function into 4 parts. So my delta x would be b minus a over n. N equals 4. So I've got 3 minus 1 over 4. So 2 over 4, or delta x equals 1/2, or 0.5, let's say. Okay. All right, so sorry, I had to cough. All right, so we have f of x sub 0. So if this thing is divided into 0.5, now my limit starts at 1. So I've got an f of 1 plus 2 times f of 1 plus delta x, so 1.5. Plus 2 times f of 1.5 plus 0.5 is f of 2, plus 2 times, so that's 1, 2, 3, this will be, well, that was my n minus 1 right there, because this is 1, 2, 3, no, I've got one more. 2 times f of 2.5, sorry, 2.5, f of 2.5, plus f of 3. So I have b minus a over 2n, so 3 minus 1 over 2 times 4 times f of 1, so 1 squared is 1, plus 2 times 1.5 squared, plus 2 times 2 squared, which is 4, plus 2 times 2.5 squared, plus 3 squared. F of 3, 3 squared is 9. Okay, so 3 minus 1 is 2. 2 over 8 is 1 over 4 times the parentheses. Okay, I worked this out. Sorry, I paused it because I needed to grab my calculator other than just working this out and doing these on the board in the sake of time. So we had f of x sub 0, we had 1 squared, which is 1, and then 2 times 1.5 squared, so they gave me this, plus 2 times 4 is 8, or 2 squared, and then 2.5 squared times 2 gave me that number, and then 3 squared, which was f of x sub n, gave me 9. So I sum all this up, I had 35. 35 times my 1/4 that I had out here gave me 8.75. Now if you take the decimal equivalent to 26 over 3, it's 8.67. So you'll see there is just a little bit of error to that. However, how do I get from that stack of numbers right there to something like this, numerical integration? It's a handy tool, it really is. So I would encourage you to read about trapezoidal rules and go through that. And as I mentioned, we'll study the error associated with these, as well as the Simpson rule. The problems that I've worked using the Simpson rule, it's a little bit more accurate, and it's a little bit different, but it's still, you go through the same motions, except that it alternates between 2 times and 4 times. It starts with 4, f of x sub 0 plus 4 times your function plus 2 times plus 4 times plus 2 times. And then it has a little bit of a different twist right out here. So, but other than that, same process, and it gives a little bit more accurate. But I want us to understand how to choose n, but n is chosen relative to the error that's associated that you're okay with. So, all right, that's numerical integration, the trapezoid rule, and study, study, study. Why are we doing this? Hey, this is real world stuff right here, okay? This is a group of data that's going to help you on the job, try to figure out how to integrate with the type of information that's coming to you. So, all right, that's all for now. Let's study and let's make a better tomorrow, and let's do that through math. So all for now. Talk to you next time. Thanks.